we're going to extend what we were working on, okay? And in some cases, we're going to look at graphs of other things first rather than just the function. So sometimes it'll be given the first derivative, and then you'll have to come up with what the second derivative might look like and what the actual function might look like. And there's a lot that's kind of involved in this. And there are also options that sometimes can happen. Like there's not necessarily just one right answer. There are certainly wrong answers, and if you, based on how you graph certain things, it can be wrong, but there are possibilities that you could have multiple correct answers as well. So, and we'll get into this more at 5.3 where you're kind of justifying what you're doing. But we'll go through this and we'll go through a few examples, and I'll give you kind of a script for how to follow this. So we're going to start with a function, and then we're going to graph the derivative, okay? So to graph the derivative graph, to sketch the derivative graph, I'm going to give you a bunch of steps to follow, and then we'll go through and follow it. It's specific, but yet there's nuance involved in a lot of it, okay? So I'll give you all these, and then we'll go through an example. All right, so the first thing you want to do is mark any zeros, okay? Of turning points or inflection points, because once you mark those on the derivative graph, you'll get a clearer sense of where your graph is going to go. And sometimes they will give you a zero, just straight up. All right, next. You're going to draw the derivative graph above the x-axis where the function is increasing. This is a concept we're going to talk a lot about. If the function itself is increasing, then the derivative is positive. And so making sure that you have your derivative graph in the right location with respect to the x-axis becomes really important in figuring out when it stops being increasing. For example, those will be easier to tell when it stops increasing and it starts decreasing. And then, of course, if we're going to draw the derivative graph above the x-axis when it's increasing, what else are we going to do that's in line with this? Yeah, so when it's decreasing, we're going to graph it below. So really what that's saying is that the function's values for the derivative's function's values are negative when the function is decreasing. The derivative's values are positive when the function is increasing. And the thing that gets tricky about this is deciding, are we talking about the function graph or are we talking about the derivative graph? Because those are two different things. Remember, the derivative graph is really a graph of all the slopes of the function, right? That's what the derivative graph is. All the the instantaneous rates of change of the function you put on a separate graph, and that ends up being okay. And then the last thing is you're going to estimate slopes. So sometimes you're going to be able to find them really easily. Other times you're going to have to kind of ballpark it. And the first example that we're going to go through, we're going to find the slopes of specific points, and then we're going to get an idea, okay, this is what the graph has to look like. But sometimes you don't have enough information from the graph, and you need to find more and more slopes to graph on your derivative graph. Because, of course, like you, we're not just trying to really sketch. We're hoping to create the actual correct derivative. We're all just kind of wired that way. And so when that happens, then, you start looking for more and more slopes to be able to graph. So this is in your book. This is example 1. So if you'd rather screenshot it from your book, feel free. I can't tell you what page it's on. I feel like it's in the 105-ish range. Is it 105 exactly? Total guess. What do you know? I did buy a lottery ticket. Oh my gosh. There's several things here that I want you to notice. Okay, this is not, this is a finite graph. Okay, this doesn't go on and on forever. We have endpoints, right? And that's going to be important in terms of our our derivative graph is also going to be finite. I guess that's really the point. We're going to estimate some of those values, but for me, the first thing I want to do is find those horizontal tangents, because then I know where the slope equals 0, right? And so, I mean, you could also investigate to the point where you go, okay, it's increasing here, decreasing here, increasing there, and you can we can see where the inflection points are. I mean, you can just see that. And so you should get a sense of what it's going to be and kind of go from there. All right, so let's just start with the horizontal tangents. How many are there? There's 2, okay? So I have one here at -2 something 1.5-ish and 2 -1.5-ish. But that doesn't really matter, right? Because what are the slopes of those lines? 0. Okay, so I have a point. I have 2 points, I guess, in that at -2, 0, and 2, 0. And that's what's here, yeah. So then I plot it. Okay. So those are the first 2 that I plot because the horizontal tangents are always the easiest ones to graph. What would you say are the next easiest slopes to kind of look for? Ones and negative ones, right? So we're looking for, we're familiar enough now with what the graph of y equals x looks like, right? It's that 45 kind of thing. So I'm looking for places where I can draw what looks to be about slopes of 1. Again, we're kind of ballparking, but we're trying to have good estimates. So here's where I come up with ones that look like 1s, right? I know that's kind of tougher to see because it's blue, but so I feel like there is a slope at 1 at where x equals 3 and where x equals -3. So then I can just plot those both at 1. How about a spot where the slope is -1? Yeah, right there at 0. Okay, got one right there at 0. And I'm drawing on these, okay, on the original function, and if this helps you to draw it like that as you plot your points on your derivative graph, do that. You certainly aren't required to do this. As we move on to 5.3, you're going to have other ways of justifying where those came from. Okay, and so that means I have a slope of -1 where x equals 0, so then I have another point. And to me, I have enough information now to sketch this graph. I mean, generally speaking, right, we could say that this could be a cubic, right? It could be, obviously, it has trig properties as well. But if I take the derivative of a cubic, then I end up getting a quadratic. If I think of this as let's say I thought of this as a sine-ish function, when I take the derivative of that, it's going to be a cosine-ish function. So in terms of feeling good about what graph I come up with, it should make sense to us that when we get something that looks parabola-ish, that we look something that looks sort of cosine-ish. Okay, so hopefully that, at least in your head, you can go, okay, this graph makes sense. Whether you look at the left graph as a cubic, or if you look at it similar to like a sine function, you should get something that looks like that. Why did I put arrows? Good question. Just because I was just feeling the flow. Let's get, well, I put them in the right spot. It really should be, I should just take the arrows off, yeah. Because the function ends where x is 3.5, and so I should really be there-ish and there-ish. That's what it should be. My bad. The trick when I try to draw it, right, you try to, I don't know the best way to describe it, when you're trying to be flowy, instead of just, straight lines, it's hard because you want to draw straight lines all the time. And of course, it's a curve, and when you're doing it by hand, and you can see, if you look closely at my graph, there's a lot of like jitteriness going on because I'm trying to be flowy, and then when you forget that there's endpoints, that'll happen sometimes. Now you're going to say, well, this is the same. Okay, no, before there's more steps. This is also when you're probably on page 105 or 106. So instead of going through them one at a time, I'll just put them all up there at once. Is this same page 105?
106.
106, okay. So now we're going the other way. They call it the antiderivative. So in other words, we're starting with the derivative function this time, and we're going to work our way back to the function itself. Okay? So we're going to make a number line to try to figure out where f is increasing and where f is decreasing. We're going to make a second derivative number line, okay, so we can figure out concavity. And then we're going to try to put that all together and draw a graph. And this is where sometimes you can get different variants and your graph would still be correct. I want to talk a little bit about one of the things that's said here. It's saying this does not involve the slopes of the derivative. What would the slopes of the derivative graph actually get you? Yeah, it'd get you the second derivative, right? Because when you take the slopes of the function, you end up with the graph of the derivative. When you take the slopes of the derivative, you end up with the second derivative, okay? And so, given you're free to shift the graph. Okay, so this part, this is where you could have variations. You can shift the graph vertically if you want to. Like, I don't know why you would, but you can, which is where you can have variations of the same graph that would represent the same first derivative and also second derivative, since those are just graphs of slopes. All right, now you're looking at this going, oh, that's the graph we just had. No, it isn't. The graph that we had, I mean it is, but the graph that we had before was the actual function. This graph is the derivative function, okay? So now if we think about this as a cubic, and we go back to the original graph, we're talking about the possibility of it being of degree 4 instead of degree 3, okay? So that's where it can get a little trickier. All right. So the first thing I'm going to do is I'm going to plot the zeros of the first derivative on my little number line, and then we're going to figure out where it's positive and negative. Okay, so this is the first step. So I've got my 0 at negative 3.5, 0, and 3.5. Those are basically my critical numbers. And I just have to look at the graph and go, okay, where's it positive, where's it negative? And of course, it's positive over here, negative over here. So we can graph that. Which means, and I'm going to try to keep reinforcing that, this means the function, the actual function f, is increasing over that interval and decreasing over this interval. Doesn't necessarily mean the function is positive or negative. This is where we get tripped up, right? This does not mean the function is positive here. It means the derivative is positive. That means the function itself is just increasing over that. It could be all in the negative region and increasing, right? Functions can increase from left to right, and still the function itself's values are negative. The same way here. We can have a decreasing function that's all positive. So don't get that confused, okay? When we talk about positive and negative of the first derivative, what we're saying is the function itself is increasing, the function itself is decreasing. Right. The next thing we need to do is figure out what's going on with the second derivative. And I'm going to present it a couple different ways. One, we have to be able to first start off with our regular numbers, right? I mean, that's kind of the numbers that we're working with. But then there's other points that we need to look at. When we talk about the second derivative, we're talking about concavity, and we're talking about inflection points. So one of the ways that you can tell where an inflection, you tell me, how can you tell without just sort of looking at the graph? What's one way to tell from the first derivative graph where the points of inflection will be. Do you remember?
For the local max.
Local max, local min, where the horizontals, the slopes are, right? So in both cases, those are saying the same thing. Okay, I have a local max here at -2, which means I have a point of inflection, and we can see that there. And we also have a point of inflection here. So I need to actually test between those intervals. And then once we figure that out, we'll have a sense of the shape of the curve, a better sense of the shape of the curve anyway, okay? So now we're looking at the slopes of this function. And of course, from here to 2, the slope of this is going to be positive. From -2 to 2, the slope will be negative. And then the slope from 2 to 3.5 will be positive. All right. So that tells us about concavity of f. All right. So from -2 to 3.5, or from -3.5 to -2, we're concave up. From -2 to 2, we're concave down. And from 2 to 3.5, we're concave up again. Now, let's see if I actually drew endpoints this time. Ish. My same issue. Okay? So now, try to sketch it. See what you come up with. Yeah, in reality, you really don't need the -3.5 and 3.5. But since that is those are endpoints again, I really should put this, let's move that over. And this one over. They really should be inside here and inside there because the graph ends at 3.5 and then -3.5. It really should be inside there. So keep in mind while you're graphing that, I have 3 spots where the first derivative is 0, which means I should have a horizontal tangent at those 3 spots. So my function at these 3 spots, the slope should be 0. Okay, that's what this is saying. Okay, so at those 3 spots, you should have a slope of 0. If it helps you, knowing where those horizontal tangents are be helpful. They also give us a point here. I guess I glossed right over that. There's a starting point of 0, 1. Okay. So they give us a point. And since we know that the slope is 0 there, I actually have a horizontal tangent here. Okay? And I also have horizontal tangents here and here. Okay? And then it's just a matter of making the graph fit to that. So the next part that I would do is deal with the concavity. So from here to here, we are concave up. And from here to here, we are concave down. Actually, from here all the way to here. And so since this is a horizontal tangent, this part from here just ends up giving me mirrored kind of upside down parabola-ish looking thing. And then I'm concave up again. Where if you want to think about it this way, one of the things you can think about is almost like there is a horizontal asymptote here and here, except this is connected. For the first side, and this time I didn't draw an arrow. All right, so we're about here at 0, and we're concave up right to -2, and then at -2 we go concave down, and then it stays concave down until I get to 2. I mean, it's basically a mirror image of that, okay? Where it kind of bottoms out. Again, the part of my graph that I'm disappointed in is that this is actually below this -2. I don't like that. But that one bothers me a little bit because they're not the same on both sides, but I feel like they should be. And essentially what you have to do is you're going to estimate some of these, well, you don't even have to estimate. Like here at -1, 1, I have a slope of 1. up a little bit higher, I guess, though. No, just the slope is 1 there. Okay, at 1, the slope is -1. Okay, at 3, the slope looks like it's about -1 again, right? So maybe I think this side is a little bit better. Maybe I flattened out too early. You see what I'm saying? Okay. But you can use these slopes to kind of estimate the steepness of the curves. Because here at -2, we're greater than 1. So this is a little bit steeper than, is 1, is steeper than 1. And at 2, we're steeper than -1. So kind of like that, right? And you're just getting ballparks here. Nobody's expecting it to be perfectly exactly. I mean, we don't have enough information to make that happen. So we want to get ourselves close. We want to make sure that we have horizontal tangents in the right places, that kind of thing. How many had something like that? Okay.
Looks so bad.
Huh?
I said mine looks so bad.
Yeah, it's all right. Again, if you can identify those key things, the points of inflection, the horizontal tangents, the estimations of the slopes, then you're going to get close. All right. Any questions before we move on to the next thing? So this time we're going to graph both the function and the derivative. Okay. So again, in the middle here we have the first derivative. We're going to come up with the function, and we're going to come up with the second derivative. And then these are the number lines. This is number 3 in your book, so you can screenshot it from there. So this portion here, that is a linear function. That forces the function to be what kind of function? What kind of function for this portion does the function, if this is linear, it has to be quadratic, right? Because this is degree 1, which means the function itself had to be degree 2 in order to get to a linear function. Now, the only thing I will tell you is you can treat this like a quadratic. It's not necessarily a quadratic, though. We don't have enough information. No one can argue that this is linear. Everyone will be like, yes, it's linear. You can't argue against it. This could be multiple degrees. It could be 4th degree, 6th degree, that kind of thing. For simplicity's sake, to be honest, I would think of it as a quadratic, because then we know that we're looking at a cubic over here. But that also allows us to gain more information about what to do for the second derivative. That's the hint I'll give. What number goes on my first derivative number line? Why? Yeah, that's where I get 0. Okay. Of course, it's positive on the right, negative on the left. So that's the decreasing, then it increases. So what else happens at, what's true about the value, what's true about the function at x equals -2? There's a what? There's a minimum. Yep, there has to be a minimum. Because the first derivative goes from decreasing to increasing, all right, I'm going to have a minimum there. So if we think about our parabola, because we've established that the graph should be a parabola, it's an upward facing parabola. It's going to have a vertex at -2. So this is that shifting vertically, right? So long as it has a horizontal tangent where x equals -2, it could be up here, it could be down here. Yeah, it could be down there too. Let's talk about the second derivative. Where is my critical point going to be on the second derivative? Yep, right there at 0. Okay, now it's obviously positive here. Okay, how about concavity of this? What do we think about it in terms of, is it, I mean, it's kind of neutral, but we could say that it's positive. Just, it's not really going to change concavity is what you want to think about. Because it doesn't really, I make it positive to match that way, because it's not going to change. It can't be negative, okay? All right, so here's what I did for the actual function. I did some shading. You don't have to do this, but then again, this is just another strategy. So in this region over here, okay, I know that the function needs to be increasing. And in this region over here, I know that the function has to be decreasing. Okay, that's sort of the key. Now, we've already discussed this. There is a relative min at x equals -2. And the other thing is that this is concave up. So we've discussed that already. So now it's just a matter of drawing the graph, and then we'll move on to the second derivative function, okay? So hopefully, and we've talked about both of these things too. We've talked about the fact that this is linear, which means I have to have a parabola over here. We're gonna say degree 2. It's not necessarily degree 2, which means that this would be degree 3. And so here's what I came up with for my graph. The first part is my parabola looking function there, because until x is 0, I have a parabola, okay? Here what I'm doing is drawing kind of a cubic. Well, since I'm only drawing a portion of a cubic, and it just has to be increasing and concave up, I just kind of made part of a cubic. So it looks like a weird parabola-ish. That's the way I did it. It's not the only thing you could have done. You could have done other things for that. Yeah.
I just thought, so for the actual function, that
Yeah.
the slope at 0, x equals 0, has to be 2 from the start, which is confusing because like this goes almost straight from the start.
Right. So it's almost like these should be the same slope.
Yeah.
Right. That's where it's tricky, but at the same time,
It's hard to draw.
yeah, it is hard to draw that. And so I wanted to, for me, when I drew this, I didn't want it to just continue and be a parabola. You know, I guess it could have looked like that, because a cubic does look like that. I wanted to distinguish, but obviously right here the slope is not 2, right? So my graph isn't great. Maybe it should look more, you know, have more of a steepness to it. But that's where it gets tricky, right? Oh, I didn't want it that big. Oh, it's not even gonna let me. So yeah, it gets a little tricky up in there, okay?
Well, you wouldn't want to make it look like a cusp, right? Because that.
Right, because it
would
needs to be
a hole.
differentiable. Yeah, exactly. You don't, right. So you don't want it to be sharp, right? You don't want it to be pointed or anything like that, because that slope still has to be 2. So yeah, I mean it's tricky to try to figure out how to make that stay 2 and still have curvature to it, right? So maybe more that way.
This is a dumb graph.
It's tricky. That's what I'm saying. That's a part of this that's tricky. And so you end up, so now, you know, if you pull further and further away from it, now it just looks like one big parabola, right?
Yeah.
So, but it should, but there again, if you think about it, if you zoom in on a particular window of a cubic, parts of cubics look parabolic. So, again, it's tricky, especially when you only have so much room to work with. Now, let's move on to the next part, because I think the second derivative is also tricky. Since we are taking the derivative of this, we are looking for the slopes of these lines, okay? The slope of this line is the same everywhere, right? What is the slope of this portion of the line? 1. The slope of this is 1. So in other words, I'm going to have a horizontal line. And if you think about it, if I take the derivative of a linear function, I end up with a constant function. So a graph of a constant function is a horizontal line. If we assume that this is degree 2, okay, then the derivative of that is going to be a linear function, okay? And so the trick is figuring out, all right, what are all the different slopes? And we've talked about it a little bit. I mean, the slope of this is 2-ish, right? Again, you're making an approximation. So from 0 to wherever, our slope is 2, and we have a linear function. And then here we have a constant function. So my constant function part, I think, is the easiest one. The slope of that is 1. And this is, again, where we lose that piece because it's going to jump up to the other one. And the other one is 2, okay? And the slope, because right here, the slope is 0. It starts off, and it's open because if we had that cusp, if we had that sharp turn, it wouldn't be differentiable anymore. And so then it goes up by 2s. I just did a regular linear graph of 2s.